Hello everyone, I'm Visharath Adhikari, a PhD candidate in mechanical engineering at Baylor University. I'm doing research under Dr. Paul Rowe. Our research is focused on the knee joint assistance for elderly people, and today I'm going to present one of our findings on knee joint muscle force variation at different walking speed and effectiveness of using the brace to improve the knee joint functionality. So to begin with, a knee is a major load-bearing joint of the human body where the peak load can vary from up to 3 to 7 times the body weight. Body weight. As the person ages, there comes several problems associated with it that could be due to muscle power or bone density decrease, tendon inflammations, biological problems, and osteoarthritis injuries like things. To know the decrease in performance better, we need to study the complex 3D joint motion of the knee and muscle force associated with it. Knee extension is achieved primarily with the help of quadriceps muscle, of flexion with the help of hamstring muscles, and rotation with the help of biceps femoris and popliteus muscles. To assist this motion, knee assistive devices are needed which can help to reduce the both joint reaction forces and muscle forces, but these assistive forces depends on the level of activity and work differently on the different muscle groups. So our study aims to study the variation in knee joint muscle forces at different level of activity. Here in we have taken walking speeds and know the effectiveness of using knee braces for these muscles groups. So to do that, we followed the experimental based approach in which we identified the major muscle groups, biceps femoris and rectus femoris. The collected EMG signals during the fast, normal, and slow walking condition, and without in both assisted and unassisted condition. The collected signal were then processed for activation calculation, and then finally muscle force reduction was calculated with the help of the activation signal. This is the experimental figure that shows a person wearing a levitation knee brace and for the assistance, and Dell's Tringo wireless EMG signal sensor for collecting the EMG signal. Now moving on to the theoretical portion, the muscle force can be calculated as a function of activation signal, physiological cross-sectional area, and specific tension of the muscle. Activation signal can be calculated with the help of collected EMG signal. So after collecting the activation signal for both unassisted and assisted condition, we can calculate the force in both condition, and finally the reduction in the force can be calculated with the help of this equation over here. Then moving on to the results, the muscle response in slow is in unassisted condition is shown in blue, in normal condition is shown in black, and fast is shown in red for both biceps femoris and rectus femoris muscle group, whereas for assisted condition is shown in blue dotted line for both the muscle group. Then we use the peak of the data, the average of the data, and peak average of the data for calculation of muscle reduction force, and found that for slow from slow to normal to fast, the advantage of using the brace is increasing. So we can conclude that the muscle force is increasing with the level of activity, which is similar for both the muscle group. The another thing we found in rectus femoris is it is helping in all the speed, but the brace is found to be worked against the muscle at the slower walking speed. As you see, there is a negative reduction percentage for biceps femoris muscles, and also you can see that there is a slow rate of change of force for rectus femoris muscles, but biceps femoris the rate of change is really high. Then moving to the conclusions, the assistive force at any specific muscle group was found to be speed dependent. This kind of brace was found to be helpful at high level of activity, but for a low uh, level of activity, or but low assistive force, for low level of activity, assistive force was low, so it was little unattractive for the low level activity. Thank you.